Hello everyone. This is part 4 for the method of undetermined coefficients. And last time we saw an example that where we used the technique of comparing the y sub c solution to the homogeneous to y sub p, the solution to the non-homogeneous, and we saw if there were duplicates that we had to multiply by a power of x, the least power of x, so that there were not any duplicates. So that shortened up the process a little bit. As I mentioned at the end of the last lecture, there's a table of trial solutions posted in Blackboard under the folder that says Exam 3 Handouts, and this just helps us to write out the proposed solution when the function is a little bit more complicated. So just a couple quick things to point out. The form of y sub p is our guess. If the function that's making it non-homogeneous is of these forms, then this is what we use as our guess. And in particular, note that if you have a squared term, so obviously if a constant, you're going to consider calling it a constant. Linear, call it linear. If it's quadratic, note there's a missing term here, but in your guess you have to include it. Okay, so even if there were the -7 were out of the picture, you'd still have to include ax squared plus bx plus c as your guess, because you have to include all possibilities whose derivatives might produce that function on the left-hand side. And so, excuse me, also with sines and cosines, if you just have one of them, you have to include both, because again, the combination of derivatives forces us to use both possibilities. And then we have all the other situations. So we'll look at a couple examples, and these definitely will be some that will be on your next exam, and I will allow you to use this table on your exam. So we can just pick these apart piece by piece. We really don't, for this particular problem, we're just saying to set it up, so you don't have to solve for the coefficients. It would be quite exhaustive to do so. So you're really not concerned about the left-hand side so much. Well, actually you are, I'm sorry. That should be the first thing we do, is to form the associated homogeneous. Let me actually go off to the side and do that here. So the associated homogeneous is y double prime minus 4y prime plus 3y equaling 0. And a characteristic equation is then r squared minus 4r plus 3 equals 0. I'm going to factor that. R minus 3, r minus 1 is 0. So r is 3 and r is 1. So then those are both real distinct roots. So the complementary solution would be c1 e to the 3x plus c2 e to the 1x, or just simply e to the x. Okay, now we have to make our guess. And our guess is going to be composed of the things that could possibly make up the functions on the right-hand side. So for the x squared term, so let's say here's our guess. For the x squared term, we're going to need an ax squared plus bx plus c. Okay, so those terms are going to come from the x squared term. For the x sine 2x term, that's where you might want to look at the table. Similar to the x cosine 3x, so number 10 on the table. Notice we need an ax plus b to accommodate the x term, and then we need a cosine, and we also need a cx plus d and a sine. Now, since we left off with the c here, I'm going to call it plus dx plus e times cosine 2x, and then plus fx plus g times the sine of 2x. And those would account for that term. And then finally, for the e to the 2x, all we need is, let's see, I left off with g, so let's call it h e to the 2x. Okay, I'm sorry for running into this here. I'll kind of try to isolate that. Okay, so then we have to make a comparison. And we can see, oh, and this is a 3x, I'm sorry. We can see that in the complementary function, so when we compare our proposed guess to the complementary function, the only thing in the complementary is e to the 3x and an e to the x, so just checking for those, we do see an e to the 3x here, so we're going to have to multiply that by x. So we're going to take our y sub p then to be the ax squared plus bx plus c plus the dx plus e times the cosine of 2x, and then plus fx plus t as a quantity times the sine of 2x, and then this h e to the 3x gets multiplied by x, so let's say hx e to the 3x. So that would be all we're looking for there. Excuse me. Just to test that you understand the concept of not having any duplications, because now there's no duplications between y sub c and y sub p. So a couple more of these questions on the next page. Okay, first thing, the associated homogeneous, and I'm going to do it underneath this time. So my associated homogeneous for this one, okay, that's the third derivative of y minus y double prime minus 12y prime is 0. Characteristic equation, r cubed minus r squared minus 12r is 0. Factor in r. We're left with r squared minus r minus 12 is 0. Continuing to factor the quadratic there. Get r minus 4, r plus 3 is 0. So r is 0, r is 4, and r is negative 3. Notice they are all real distinct roots. So we have y equals y sub c is equal to c1 e to the 0x, so just c1 plus c2 e to the 4x plus c3 e to the negative 3x. Alright, and so then we'll come up here for our guess. And the y sub p then, just take it term by term. The first term is just x, so for that we need to use ax plus b. and the second term is x e to the negative 3x. So if you look at the table, x e to the negative 3x is similar to number 7. So we need to use ax plus b times that exponential factor. So this would be, since we left off with b, let's do cx plus d times e to the negative 3x. Okay, so that takes care of our guess, and now we compare. And you can just again compare factor by factor. And so we do see a constant term, C1. So therefore, there can be no constant term in the proposed solution for the non-homogeneous y sub p. So to account for that, we're going to multiply the quantity ax plus b times x. And then we see that we have a factor of e to the negative 3x, which would account for d e to the negative 3x, which is the same as c3 e to the negative 3x. So in a similar way, we're going to multiply that by x as well. So then finally we're going to take y sub p to be equal to, you can distribute the x if you like, maybe call it ax squared plus bx, and then plus, I'll distribute the x inside here, cx squared plus dx times e to the negative 3x. Okay, moving on. Here we've got y to the 5th minus y cubed. Excuse me, it's not y to the 5th. It's the 5th derivative of y minus the 3rd derivative of y. So the associated homogeneous is that set equal to 0. You can, as I've mentioned before, jump right to the characteristic equation if you like. So r to the 5th minus r cubed is 0. Factor out an r cubed. Left with r squared minus 1 is 0. You could actually factor this as r minus 1, r plus 1. Or if you wanted to isolate the r squared, that's fine as well. Alright, so we get r cubed is 0. And then we get r is minus 1 is 0. And r plus 1 is 0. So here we get r is 1, r is negative 1, but here r is 0 with a multiplicity of 3. Okay, so that's very important, because when we write our complementary solution now, let's put it over here, remember, we're going to need, when we have multiple roots, we start with C1, and then we pick up an x term in each of the subsequent factors, so plus C2x plus C3x, and then times e to that common root, in this case 0x. And then we need a plus, let's call it C4 e to the 1x, and then plus C5 e to the negative 1x. And so let's get rid of that e to the 0x, we'll just call it C1 plus C2x plus 3cx squared plus C4 e to the x plus C5 e to the negative x. Okay, so then back up here, we're going to make our guess. So from this, our guess for y sub p is, okay, we've got an e to the x, so we need a e to the x. And then we got an x squared minus 1. So, remember, we're going to include all possibilities. So, bx squared plus cx plus d. And then when we compare our proposed guess to the solution to the homogeneous, we see, first off, let's look at the a e to the x. Is there an e to the x in here? And yes, there is. C4 e to the x. So we're going to have to multiply this guy by x. But then we're going to consider all these simultaneously. The bx squared plus cx plus d. And we're comparing them to these terms here, the c1, c2x plus c3x squared. If there can be no duplications, then the smallest power of x, if we just multiply this by an x, we'd get x cubed, which would be fine, but then we'd get x squared and a dx, which match, so that's not good. So then we'd go up to x squared, and that'd be x to the fourth, which is good, x cubed, which would be good, excuse me, but an x squared, which would still be a duplication. So therefore, to guarantee there are no duplications, we have to multiply that by x cubed. So then we're going to take our y sub p to be equal to ax e to the x, then plus multiplying these by x cubed, bx to the fifth, plus cx to the fourth, plus dx cubed. And now note that there's no duplications between terms. Alright, so then for the final example here, we've got y double prime, so the associated homogeneous again, y double prime minus 6y prime plus 13y is 0, characteristic equation, r squared minus 6r plus 13 is 0, and it turns out that this does not factor. We're going to need the quadratic formula. So r is minus b, so minus of minus 6, plus or minus square root b squared, so minus 6 squared, minus 4 times a, which is 1, times c, which is 13, all over 2 times a, which is 1. So that gives r is equal to 6 plus or minus square root of, okay, let's see, that's positive 36, here's a minus 52, so therefore a minus 16 over 2, which would be 6 plus or minus 4i over 2. Remember, get it in a plus bi form, so divide the 2 in here, we get 3 plus or minus 2i. So then recall the theorem for complex conjugate roots. The solution is going to be e to the ax, so e to the 3x in this case, and then times c1 cosine bx, so c1 cosine 2x, plus c2 sine of 2x. Okay, so then come back up here and we guess at y sub p. And there's only one factor here, but it's pretty complicated looking because it contains an x, an e, and a psi. So this is where you might want to consider the table. And And this is actually number 12, the most complicated, including all the different classes of functions. So this is what we need. So we need an ax plus b to accommodate the linear factor, an e and a cosine to accommodate the exponential and the trig. But then we need another term as well, because remember, if you have one cosine or sine, you got to have the other in your guess as well. And so, therefore, our proposed guess is ax plus b e to the 3x sine 2x, and then plus, well, let me make that cosine 2x just to be consistent with the table. It really doesn't matter what order you put them in, but, and then plus cx plus d times e to the 3x sine of 2x. Okay, and then if we make the comparison, here I didn't draw the little arrow, but up here if you want to go back up there and write compare, just to be consistent. If we make the comparison, we see we have duplications. There's the e and a cosine, as well as an e and a sine. So that would be basically taking into account this duplication of b e to the e and cosine and d e and sine. And if we just multiply by x, that'll alleviate us from having any duplications. So the whole thing we can consider multiplied by x. And so finally we're going to take y sub p to be equal to, and I'm going to multiply it inside the parentheses, as we've done in the past there. So ax squared plus bx e to the 3x cosine 2x, and then plus cx squared plus dx e to the 3x sine of 2x. Okay, so it looks like we're going to need one more part, because we're on the 22-minute mark for this now. And so what we'll do is we'll come back and finally finish up wrapping everything up with initial value problems, so it kind of summarizes everything at once. So we're going to need a part 5 for this. So we'll see you in a bit.